Hey guys, today we're going to take a further look at energy and how energy is conserved in all scenarios. Just like with momentum and mass, energy must be conserved within a closed system. This means that the types of energies can change, but the sum of all energies must remain the same. So for example, if we have a total of 100 joules of energy, we can have it split up between 50-50 of Ke and Peg. We can have 75-25. We can have 10 and 90. It doesn't matter as long as they always add up to the same total. So mechanical energy is the energy based on location and motion of the object. We calculate mechanical energy by adding the kinetic and potential energies in a system. The total mechanical energy must remain constant. So we have this equation at the very bottom of the slide. This is the equation we're going to go back to at all points during this unit. Mechanical energy is Ke plus Peg plus Pee. So for example, if we have a little girl going down a slide, at the very top of the slide, she has all Peg. And if she has 10 joules of Peg at the top, she must have 10 joules of some type of energy at the bottom. So it doesn't matter where on the slide she is, we can take her kinetic energy, her energy due to gravity, and her elastic energy, if applicable, and add them up, and they're always going to equal the total of 10. Now, another way you may see this equation is total energy is Ke plus Peg plus Pee. They are interchangeable, and it just depends upon what I'm thinking about at the time. Mechanical energy is correct. Total energy is also correct. So we're going to use energy bar charts in order to show how the different energies are distributed in any given situation. In example 1, we have a diver on a high dive. At the very top position, he is not currently moving, so all of his energy is gravitational potential energy. If it would have been a spring diving board, he would have gravity, a little bit of elastic, and a little bit of kinetic. At this point, we are about halfway down, so he is falling, and he still has a height. So we have 1, 2, 3, 4, a little bit more than 4. Let's pretend that I stopped drawing here. So we have 4 bar chart areas of energy. We're going to put 2 in gravity and 2 in kinetic, because at about halfway point, he's 50-50. Now at the very bottom, we are going to use the top of the water as the 0 height. His height is 0, so that means he has no gravitational potential energy, and all of his energy is now kinetic. So notice I'm not using numbers at all. All I'm doing is distributing 50-50, 75-25. We are breaking apart the 100% of energy into whatever parts are currently there. So here's a second example. A crate is being propelled up a hill by a spring. So in the first picture, if this is our 0 height, we have 0 gravitational energy. Since this is not currently moving, we have 0 kinetic energy, and all of our energy happens to be elastic. Now at this position, we are no longer touching the spring, so we have 0 elastic energy. We have about 50-50 kinetic and gravity. And then at this very top point, we have more gravitational energy because we are taller, but since we have whooshies behind our box, we have these little lines that indicate motion, we are still moving. So maybe we only have 1 box of kinetic and 3 boxes of gravitational potential. So again, not paying attention to any numbers, just breaking them apart in percentages. And now our last example. We have a science cart rolling onto carpet. So in this first picture, we have kinetic energy present. And that's the only energy that is there, so I'm going to put all of my boxes under kinetic. Now in the second one, let's say the height did change a little bit, so maybe I have a half a block of height, but my kinetic energy is lower because my whooshies are smaller. So let's say I have 2 blocks of kinetic. Now in the third picture, I still have that half a block of height, but now I'm not moving at all. So my kinetic energy is now 0. So is the total energy staying the same in this picture? The answer is no, because our bars do not add to the same total. Now we can show that by adding a fourth column to this bar chart, and that column is the work column. So if I have 2 blocks here and a half a block here, at this point I have 1.5 blocks of work, and at this point I have 3.5 blocks of work. So work is a way that we can indicate that maybe there's friction present, or you're making a noise as it's traveling. If you seem to be losing energy, it's because it is going to another form of energy that isn't mechanical. So by adding that fourth column, we can indicate that that energy is still going somewhere, but maybe it's not going to making it go faster. Maybe it's going to heat due to friction. So the total energy is neither increased nor decreased in any process. Energy can be transformed from one form to another, and when energy appears to be removed from the system, work can be used to account for this transfer of energy. And that's just into one of the other types of heat energy, sound energy, light energy. So we're going to do a practice problem with some math. Susie has a mass of 50 kilograms and sits atop a 7-meter tall slide. What is her velocity once she reaches the ground? So I'm going to draw a picture over here, and we're going to make this a special slide that actually ends at ground level. Okay, and we have the top and we have the ending. So I'm going to write mechanical energy at top and mechanical energy at the bottom. At the top, she only has potential energy due to gravity. Because if we had our bar charts, at this point she is not moving, there is nothing elastic present, so it is only PEG. The mechanical energy at the bottom, her height is 0, there is no elastic energy present, would be only KE. So ME at the top is mass times gravity times height. The mass is 50, gravity is 9.8, and height is 7. The mechanical energy at the top is 3,430 joules. So the mechanical energy at the bottom must be the same total. So 3,430 joules is equal to 1/2 mv squared. And I know her mass is 50, so I'm going to solve for v squared. V squared is 137.2. And my last step is square rooting it, and her velocity at the bottom of that slide is 11.7 meters per second. So we used the mechanical energy at the top and the mechanical energy at the bottom, set them equal to the types of energy present to solve for our unknown. Now in the next problem, I'm going to do this in one section instead of 2 sections, and hopefully it'll make sense. So Susie has a mass of 50 kilograms and she sits atop a 7-meter tall slide. That's the same as before. What is her velocity when her height is 2 meters above the ground? So if this is our picture, we have that special slide that ends at the ground. This is our before placement, and this is our after placement. So at the top, she has PEG only. Her mechanical energy at 2 meters, she now has PEG and KE. So what I'm going to do, since these have to be equal, I'm just going to set the actual equation parts equal to each other. So her mass times gravity times the height at the top is equal to her mass times gravity times height at 2 plus 1/2 mv squared. Her mass is 50, gravity is 9.8, and at the top her height is 7. Her mass is 50, gravity is 9.8, and at the second location her height is 2. Her mass is 50, and we do not know her velocity. At this point, do the numbers. Just mathematically work out these sides of the equation. The left is still 3,430. 50 times 9.8 times 2 is 980, plus 25v squared. Now I want to solve for v, so I have to get this 980 over to the other side. I'm going to subtract it from 3,430, and that gives me 2,450 equals 25v squared. Now I'm going to divide both sides by 25, and v squared equals 98. And I'm going to square root both sides, and v equals 9.9 meters per second. So at this height of 2 meters, her speed is less than what it was at the very, very bottom. That should make sense. So tomorrow in class, what we're going to be doing is practicing with this whole idea of mechanical energy being conserved. We're going to be given different scenarios where we have different knowns and unknowns, where we're solving for something that isn't given to us using the idea of this conservation of energy. See you tomorrow.